Good afternoon. Welcome to the fifth lecture of radio frequency IC design. In today's class, we'll continue the discussion on the effects of nonlinearity. So, just to look at what we have discussed in the previous day, uh, we discussed on one another effect. In the first class, we have looked at harmonics, one effect of nonlinearity. We also saw the simulation and we saw that as your input amplitude or your input signal level increases, the harmonic components amplitude are also increasing, and that was one of the observations what we made. uh, right, the magnitude of nth harmonic grows in proportional to the nth power of input amplitude, right. That was in harmonics, and in yesterday's class we looked at something called as gain compression. So for any nonlinear system, your gain will eventually compress, even if some of the devices show expansive behavior. Due to the power supply limitations, whatever may be the response obtained from the device SCADA, ultimately your gain will compress, and that we studied like this. And this phenomena is called as gain compression. And since this is an effect of nonlinearity, we introduced a performance metric to characterize this nonlinearity, and that is 1 dB compression point. We obtained a mathematical expression for that, and also we saw how to simulate this in cadence. So we obtained 1 dB compression point referring to the input side in this form. Now in today's class, we'll continue and we will continue on this discussion of nonlinearity. So just an announcement, if uh, keep yourselves in mute. I'm getting a small noise from. So is there any background noise uh, from my side? Can I get a response in the chat box? Okay, thank you. Yes. Okay. Fine. So we will start. We'll continue the discussion on the effect of nonlinearity, and today is a third after harmonics gain compression. This is a continuation of this gain compression, and let me just give the title as desensitization. So we will look at this in a bit detail. Uh, yeah. So far we discussed about gain compression. Now, um, so we will look this. What I'm going to discuss today is actually one effect of this gain compression. So to understand this, let me take this example where we have. Yeah. So I am considering again a nonlinear system. So system is nonlinear. Input and output are applied to the system. Now assume that through an antenna is picking the input signal and it is available to the first stage. You can assume that it is an amplifier or whatever it is. So in the previous two discussions, we have taken we were looking at the input signal. So now we will consider one another case, one different case, where this is your input signal x of t and this is your output y of t. Now instead of considering only input at the only the desired signal at the input side, as in one of our previous classes I mentioned that antenna will be receiving a whole bunch of signals, right. It will definitely have desired signals and it will have some undesired signals, or the signals which are transmitted by other transmitters to some other receivers. So if I am considering that case, say you have a desired signal, say that desired signal, why I'm showing this representation is to show that this is a modulated signal. Some information is coming through this, and say this is at frequency of angular frequency of omega 1 with an amplitude of a1, which is a desired signal. But along with this desired signal, I am considering one undesired signal. So I'll mark it as an like this, where this undesired signal is located at omega 2 with an amplitude of A2, right? So we generally call this undesired signal as interference, right? So what I'm considering now is there is a nonlinear system, and at the input of this nonlinear system, along with the desired signal, this system is accepting an interference signal also at a slightly different frequency omega 2 with an amplitude of A2. Now, what happens if this system accept these two signals? One is a desired signal and the other one is a undesired, or other one is an interferer. So what happens, or how do we analyze this? So we will continue to analyze this in the light of this non-linearity. So what I can do here is, so maybe I'll write this x of t as a1 cos omega 1t plus a2 cos omega 2t. This is how we consider, where we know that a2 or a2 cos omega 2t is the interferer signal. Now, if by two-tone test in our initial classes, by two-tone test, we know that when two different frequencies are coming into a nonlinear system, we know the products coming at the output. Say, so if I write y of t here, mm, I'll refer back to that, the output, yes. So if the input is a1 cos omega 1t plus a2 cos omega 2t, I will definitely get a lot of components. Again, we are not looking at the harmonics or the intermodulation products. We are looking at only at the fundamental gain term and how that fundamental gain term is affecting because of the presence of this interferer. I hope you are getting getting a clarity on what I'm talking here. So whenever two signals are appearing at the input of a nonlinear system, you will have a lot of components like harmonics, intermodulation, and many other components will be there. But again, for this discussion, I am not considering harmonics or any other sum or difference products or any other intermodulation products. Rather, I am looking at the fundamental gain term. So if you refer back to the analysis what we have done from the polynomial, I can write y of t expression as y of t can be written in this form. How will I write y of t? Y of t can be written as alpha 1 plus 3 by 4 alpha 3 3 by 4 alpha 3 a1 square plus 3 by 2 alpha 3 a2 square. This is a fundamental term into a1 cos omega 1t, right? So in the presence of two signals, if I look at the output fundamental component, the coefficient of this coefficient coming along with the input signal will be alpha 1 plus 3 by 4 alpha 3 a1 square plus 3 by 2 alpha 3 a2 square. Now say for example say that this a1 so if I look at the input signal, the desired signal and the interferer, it is clear that I have taken a case where you have a strong, very strong interferer and you have a weak desired signal. So how will I understand that? By looking at the signal level. So this is weak and this is strong. So I can say that a1, the value of a1 is comparatively very less with respect to a2. a1 is very less compared to a2. Right. If that is the case, if a1 is small with respect to a2, then definitely I can do one thing here, because if I expand this, or if I take a1 inside, I have a term called alpha 1a, then 3 by 4 alpha 3 a1 cube and 3 by 2 alpha 3 a2 square into a1. So if a1 is very small, a1 cube will be smaller, and for that I'll just neglect this term, because a1 cube is very small. Are you guys with me? Can I get response in chat box? All right. Okay. Thank you. Yes. So a1 cube is very small, so I'm neglecting that. So after neglecting this, if I write the output equation for y of t, I can write this equal to alpha 1, or I'll just write approximate because I am neglecting one term. So I will write this as alpha 1 plus 3 by 2 alpha 3 a2 square into a1 cos omega 1t, right? This is y of t. Why neglecting a1 cube? Because a1 is very small. Now, so as I told, this is the continuation of gain compression. I'll assume that here also the value of alpha 3 is negative. Alpha 3 is actually taking a negative value. That means this device or the system is also showing a compressive behavior. That means I can further write this y of t as alpha 1 minus 3 by 2 alpha 3 a2 square. Just a minute. Hello, sorry for the delay. Yes, Rakshak, I saw your one second. We are neglecting a1 and not alpha 1. What is that? Rakshak, can you answer?
Like in y of t,
Yeah.
in y of t, a1 is less than a2. That's why compared to a2, a1 cube is so that term is neglected. But a1 will usually a greater because that is a gain term or
Yeah,
those will be weaker only, most of alpha
I
1
got
and
it. So I did not neglect a1. Yes, I didn't do that.
no sir, we can neglect alpha 1 also because a2 is no, sir.
Rakshak, actually your voice is breaking. So what I'll just explain what I'm doing here. So what I did here is, since a1 is small compared to a2, a1 cube is what I'm neglecting. So that means basically it is affecting this term. But alpha 1a term is a significant term, right? It is not a cubic term. It is alpha 1a is a significant term then. I hope it is clear for you. Yeah, okay, yes. I haven't completed writing this. So it is alpha 1 minus 3 by 2 alpha 3 a2 square into, yeah, 3 by 2 alpha 3 a2 square into a1 cos a1 cos omega 1t. At alpha 1 minus 3 by 2 alpha 3 a2 square into a1 cos omega 1t. Now if I look at this this output expression, or so what you are seeing here being inside this bracket is nothing but the gain which is available to the desired signal. Now I can see that this gain this gain is actually a decreasing function. Gain is actually a decreasing function, of A2, right? So by looking at this, the gain part, the fundamental gain part, what I understand is your gain is actually so if A2 increases, your gain is going to decrease. The effective gain which is available for the fundamental signal is going to decrease. That is why I stated here as gain is a decreasing function of A2, right? So that means what will happen, say at a large, very large A2, at a large value of A2, if this term, the term which this term, so as A2 keep on increasing, this term can be equal to this alpha 1A, or in that case this gain can be, the gain of the desired signal also can be reduced even to 0. So as I keep on increasing A2 value, whenever this the term which is marked here, when it becomes equal to the fundamental gain term alpha 1, even the entire gain of the system can be reduced down to 0. This specific condition, so when an interferer is coming in, and when an interferer amplitude is becoming, when it is becoming sufficiently large, the gain dropping down to 0, this phenomena is otherwise called as desensitization. Why? Because this interferer signal is basically desensitizing the main circuit here, because the desired signal is not getting amplified, and the gain of the system is desensitized by the interferer signal. So in such case, we call this interferer as, so if this happens because of an interferer signal, we call this interferer as blocker, or we call it as a blocking signal. We call this as a blocker or a blocking signal. So this blocker or blocking signal refers to the interferer that desensitizes circuit, and thereby reducing the gain ultimately to 0. So even if it is not reduced to 0, we generally call this interferer which affect the gain, the fundamental gain component of a desired signal, as a blocker or a blocking signal, right? So this is one of the extension of the gain compression what we have seen just now. Right. I hope this is clear. Now, to make it more clear, let us take a simple numerical. I'll take questions. All right. Akash, I saw your question only now. I did not follow why alpha 3 is negative. I don't know whether you attended my yesterday's class. If you attended my, did you attend my class yesterday, Akash? Can I get response? No. All right. So please refer back to the video, yesterday's video. We have discussed the two phenomena. One is called as gain compression, and another one is called as something called as expansive characteristics shown by certain systems. Now, if I assume that there is gain compression, the value of alpha 3 is actually negative, right? So that is a this alpha 3 is negative, and I'm assuming that the system is showing a compressive behavior, right? So that is the reason alpha 3 is considered as negative. Alpha 3 terms are nonlinear terms, so if it will be removed due to A2, good only. Yes, Akshay, alpha 3 terms are nonlinear terms. Yes. Now what is happening here? So there is an external signal. So at this point we haven't we have neglected the other nonlinear effects. We have the nonlinear effect of harmonics, we have the nonlinear effect of intermodulation. All those things are present, right? But we are just looking at the fundamental gain term, and what we observed is because of this interferer, at some point of time the signal, even the desired signal is not getting magnified, or the desired signal, your system is becoming desensitized. The system will not respond even to a desired signal, so that cannot be considered as a good thing, right? So by becoming 3 by 2 alpha 3 a2 square equal to alpha 1 will is fundamentally what it is doing is actually reducing your gain to 0. That cannot be considered as a good thing, right? So I hope you understood, Akshay. Uh, okay, yes, thank you. Okay, let us see this question. Uh, Please note on this question. An LNA, and that is modeled using an equation y of t equals alpha 1 x of t plus alpha 2 x square t plus alpha 3 x cube of t. Now, given that alpha 1 is equal to 10, alpha 2 is equal to minus 2, alpha 3 is equal to minus 0.5. These are the values given. Now, the input to this LNA are there is a desired signal that is at omega 1, which is having a peak amplitude of 1 milli, and there is a blocking signal at omega 2, which is having a peak amplitude of 2 volt. Now, so there is an LNA which is modeled using this. The coefficients are given, alpha 1, alpha 2, alpha 3 are given. The input to this LNA, there is a desired signal which is at omega 1 with a peak amplitude of 1 milli, and there is a blocking signal with a peak amplitude of 2 volts. Now the question is, assume that there is no filtering before this LNA. That means the interferer is directly present at the input of this LNA. In that case, what is the gain of the desired signal? That is yeah, so you can find out what the answer to this question. After discussing that, we will I'll give you the next part of the question, right? So yeah, while doing this, if you have any doubts, what we processed, yes, Anirudh, can you just unmute and tell me how did you get that 7 volts per volts?
Sir, there's the gain formula, which is alpha 1 plus 3 by 4 alpha 3 a1 square plus 3 by 2 alpha 3 a2 square. But
Okay.
since alpha 1 square will be negligible compared to the other terms, if we
Mm.
substitute the values, we'll get 7 volts.
How come alpha 1 square, from where this alpha 1 square term is coming?
Sorry, a1 square, I'm sorry. Yeah.
Okay, a1 square.
So a1 square is, in this case, it will be 1 millivolt. And if you square
Mm.
that, it will become 10 power minus 6.
Okay.
So if we do alpha 1, we get 10 plus 3 by 2 times alpha 3, which
Okay.
is minus 3 by 4 into 2 volts.
Okay. Yes. And
Sorry, 2 volts into 2 volts, which is 4, sir. So we get um, 10 minus 3, sir. We get 7 volts per volt.
okay, so so without neglecting that a1 square term, can you just tell me what is the answer?
Yes, sir.
Yeah. So others also please work and just let me know the amplitude or the gain.
So we get 6.99, sir.
All right, all right. There is no much difference, right? Because the square
Yes,
term is 1 micro. Yeah. Thank you,
yes.
Andit. Yeah. So can I get answers even from others? So for others who did not understand this, I'll just let you know. This is how the LNA is modeled as, and these are the constants given: alpha 1, alpha 2, and alpha 3. Now what you can think is, you have an LNA, there is no filter before this LNA. That means directly this LNA is receiving signal. What are the signals at the input of this LNA? There are two signals. One is a signal at omega 1 with a peak amplitude of 1 milli. Another is a signal at omega 2 with a peak amplitude of say 2 volts. Right. Now this system is non-linear. So since the system is non-linear, I can write the gain of the system. So how will I write the gain? So for this you can refer back to the first analysis what we have done, and from there you can actually pick the coefficients to get the gain value. So if others are calculating, just put your answers in chat box. Or if you got this answer as 7 volts per volts, then also you can respond as yes. Right. So gain of desired signal can be written as alpha 1 plus 3 by 4 alpha 3 a1 square plus 3 by 2 alpha 3 a2 square. Now yeah, this is the gain, this is the coefficient what you are getting. Now if you substitute the values for alpha 1, alpha 2, alpha 3, there is no alpha 2, yes, alpha 1, alpha 3 and a1 and a2, you will end up with this value which is very close to 6.99 or 7 volts, right? So this is your gain of the desired signal. Now I hope it is clear. If it is not clear, I'll give you can ask now, or I'll open for the discussion at the end of the class. Right. Now the second part of the question is, now this happened when there is no filtering, or there was no filter before LNA, and the signal, the interferer and the desired signal is directly arriving at the input of this LNA. Now the next part of the question is, if we are inserting a filter before this LNA, that is basically to filter out the interferer component, and the minimum gain for the desired signal is say 19.5 decibels. The question is, by how many dBs must the filter attenuate the blocking signal or the interferer? Maybe you can read question once again, and you can give an explanation, like you can think, and you can continue for solving it. So now before LNA there is a filter, and for that filter and the minimum gain need for the desired signal is 19.5 dB altogether. The LNA has to provide a gain of 19.5 dB to the desired signal. Now the question is, by how many dBs must the filter attenuate the blocking signal? So what should be the attenuation? What should be the attenuation that should be given to the blocking signal? Yes. Yes, Anirudh. Answer, yeah, attenuation should be, it is attenuation, yeah, right. It is 7.3. Yes. Any answers? Anyone else got the same answer? Okay, I'll explain this. Others can try. I'll explain how to do this. Now, in this case, what I have is a filter just before the LNA. So there is a filter here, and after filter, we have the LNA block. Right. Now, one thing, when a filter is introduced, one more information is given. The minimum gain for the desired signal is 19.5 dB. That means this LNA is providing a gain of 19.5 dB. right? Now if you look at the input side, you have two signals here. One is at omega 1, another one is at omega 2. This is 1 millivolt, this is 2 volts, right, where this is A1 and this is A2. Right. Now, since a filter is present there, filter will in fact filter will filter out the component which is an undesired component. For that, filter will be designed for with respect to that particular frequency. So we do not have information on that part, but what we know is the question is, if we insert a filter before LNA and the minimum gain of this LNA is 19.5 dB, by how many dBs must the filter attenuate the blocking signal? That means we know what is the value of A2 here. The value of A2 at this point is 2 volts, right? Yeah. Now we should find how many dBs does this filter attenuate this A2 signal. That means I should find the value of A2 at the output side. If I mark it as A2 dash, what should be the attenuation given to this A2, given to this interferer by the filter? That is a question, right? So whether you are getting answers, others are getting answers. All right. Okay. Okay. Yes. So how will you get it? So when you talk about the gain of this LNA, so how will you write the gain for this LNA? Now the input to the LNA, at the input of LNA you have A2 dash and your desired signal A1, where your A2 dash is the filtered version of your A2. So by considering the minimum gain of LNA, which is given as G LNA minimum, the value is alpha 1 plus 3 by 4 alpha 3 A1 square plus 3 by 2 alpha 3. It is not A2, but it is A2 dash because it is filtered component now, A2 dash square. And that is given as what is the value? 19.5 dB. So 19.5 dB is equal to what is the value in volts per volts? All right, it is close to 9. Is close to 9.44, right? Is 9.44 V bar V. Now with this, now I know that the value of alpha 1 is known, alpha 3 is known, A1 is known, alpha 3, only A2 dash is unknown, and we can find what is A2 dash. And if you find A2 dash, what is the value of A2 dash? What value you are getting for A2 dash? Yeah, it is close to 0.86. 0.86 is the amplitude A2 dash value, right? I hope this is clear. I have taken the gain expression for LNA. Only one change is made because at the input of LNA, since your A2 is filtered, I am using the new notation as A2 dash, and from that I am finding A2 dash, and A2 dash value is equal to 0.86, right? Now so now I can find the gain of the filter. Gain of the filter is nothing but gain and attenuation both are same. If we are writing it as gain, we will just give a negative sign. So how will you find the gain of the filter? Gain of the filter can be obtained by dividing A2 dash by A2. Or this is what we are interested, like, right, like how many decibels should your filter cut down your interference signal. So A2 dash by A2, which is equal to 0.86 divided by A2 is 2, which is close to 0.4 0.43, and if you convert this, you will get to know that this is equal to 7.2 dB, or I should put a minus sign over here just to indicate that the gain of the filter will be negative, or you can write attenuation as 7.2, right? So this is how you can solve this numerical and find the attenuation provided by the filter on the interferer signal. Now, if you have doubts, I can take a few doubts, or else I'll give one more numerical. All right, I'll take questions at the end. Just I'll give you one more question, one more numerical I'll give. Probably this I'll ask you to do as a homework, or let us see. So the question is, there is a 900 megahertz GSM transmitter which is delivering a power of 10 watts to the antenna. Now the question is, by how much must the second harmonic signal of the signal be filtered so that it does not desensitize 1.8 gigahertz receiver having 1 dB compression point, say I'll give in terms of power. So 1 dB compression point is minus 25 dBm. Right. The question is, there is a 900 megahertz transmitter which is delivering a power of 10 watts. Now, so when I say 900 megahertz, the harmonics will be available at second, third, and higher frequencies. So second harmonic will be definitely at 1.8 gigahertz. Now, there is another receiver which operates at 1.8 gigahertz. Now the question is, by how much must the second harmonic of the signal of this particular transmitter be filtered out so that this will not affect the 1.8 gigahertz receiver, which is having a 1 dB compression point of minus 25 dBm. Right. One more information is given. You can make an assumption that the receiver is say 1 meter away from 1 meter away, and the 1.8 gigahertz signal is attenuated by 10 dB as it propagates across this distance. Right. I hope the question is clear. So let me just give this picture. You have an amplifier, you have a transmitter. So transmitter means the final stage will be a power amplifier. So this is a transmitter which is operating at, say, at 900 megahertz, and this is delivering some power, say 10 watts. Now at a distance of 1 meter, say you have a receiver. So receiver, your first stage is say an LNA, and this receiver is operating at 1.8 gigahertz. Now one information is given, this receiver is having a 1 dB compression point of minus 25 dBm. Now the second harmonic of this transmitter, by how much must the second harmonic of this transmitter be filtered so that this will not affect, or this will not desensitize the receiver. Right. So this includes the concepts what we learned in harmonics, in gain compression, as well as desensitization. So any answers? All right. So you can try this, and you can tell me the answer in the next class. All right. So With this, I'm winding up for today's class, and now I'll open for discussion. We'll continue with the next nonlinearity and the effect in our next class. Right. Thank you for joining, and I have 50 participants. Right.